Now that you're familiar with the pre-processing steps that we have used to convert the solar.csv data, raw data from the IoT panel, let's figure out how we feed it into our models. We have already said that we are going to look into the data for only 14 time points per day, and we use a value of 20,000 to normalize the input into 0 to 1 range. Then we call the generate solar data to read the data from this solar.csv file. Here's a small utility that would allow us to sample data sets from these data X and Y values, the input and the corresponding label values that have been read from the input data in batch size of 14 times 10, which is 140. You can play around with that value. And the data looks exactly like we have discussed in the previous video, where there are different individual readings for the time point at which we are recording from the solar panel, and the corresponding output, which is the power generated for that particular day, aggregated over the entire day. So in this case, you can see that these are different time instances for a given day, and these numbers are the same because the total amount of current generated for that particular day is the same. But if you go and change these indices to something else, which I would encourage you to do so, you can figure out that these numbers change, and so does these numbers as well. But at the end of the day, the values of X and the corresponding Ys are what is needed for us. At that point, the notion of time, the specific date, doesn't make any difference. The network learns how to predict this Ys given any instances of these X's, which is a sequence with length of 8 to 14. Here is our LSTM network setup. Note that we do not specify the maximum length as a part of our model, and we do not need to pad our variable length sequences. So the sequences can be of length from 8 to 14, and we do not have to pad zeros or any other values to our sequences that are less than 14. The toolkit automatically takes care of that. In this case, we will have the LSTM cells hidden dimension, or the internal state that we have referred to a certain values. You can play around with it. In this case, coincidentally, it happens so that 14 seems to be a pretty decent number. You can try out different numbers for the hidden dimensions of the LSTM cells. This figure should be quite familiar to you, where the individual data points are input to the LSTM cells. This is part of the recurrence units. And we just sample the output from the last LSTM cell, and then we add a little bit of a dropout to prevent overfitting, and then project the output to a single value, which corresponds to the predicted output of the solar panel based on the input values that we have here. The network code is a direct translation of what the figure you have seen before. We have a set of recurrences with each of the cells being LSTMs and their internal state being hidden dimensions of 14. We sample the data, or we pick up the data rather, from the last cell, pass it through a dropout, and then project our predicted value of the solar panel output here. Once we have the model, then we are going to train. This is, again, much too familiar to you, except for the fact, in this case, instead of just c.input underscore variable, you have a c.sequence.input underscore variable. This is important because we are dealing with sequence data. We get our model here, and the corresponding labels are also a set of scalars for this particular set of input values. Okay. We set a learning rate, a fixed learning rate in this case, and we create a schedule, learning rate schedule. In many applications, you may want to explore with different learning rates and different learning rate schedules. You can try these things out in this tutorial if you want to. Our loss function in this case is different from what we have been using for the MNIST data, because that task was for classification. In this case, it's a regression. So we use a squared error where we minimize the difference between the predicted solar panel output and the observed output of the solar panel. And the same is used for the error function. Then we can instantiate our trainer object. Once the trainer object is instantiated, then you can run through the entire data set, and you can train the parameters of the model by calling trainer.train_minibatch, by feeding the corresponding mini-batch features and the corresponding labels. This notebook is going to take a while to run, and once it's done, in this case, you can see that the loss in general reduces quite a bit. Here is the plot of how the training progresses over the number of different iterations. And you can then start plotting the mean square error for the training, validation, and test data here. And finally, you can visualize the predictions. Here you can see that the blue is the raw observations and the orange one is the predictions. And in general, they are pretty close. Even with 200 iterations is what we had started off. Let me quickly check if it was, we have trained this one for 200 iterations. Let me quickly check that. Yes, it is indeed 200 passes that we have used. But if you were to use a much larger amount of training, which is set to 2000, then you will see these curves becoming even closer to the observed values. With that, you are ready to do the assignments associated with this lab.